Hello and welcome back to Calculus 2, section 10.7, part 2, root and ratio test. So last time we did the ratio test where we said that we can extract an from the series, create an plus one term, stuff it into the limit like that, and if the limit is less than 1, the series would converge. If the limit is more than 1, it would diverge. And if the answer is exactly 1, the test is inconclusive. We did a couple of problems. I just want to do one more so we can see ratio test in action, and then we'll talk about the root test. So one more problem, ratio test. Say you have summation of, and let's go with negative 1 to the n, n to the, I don't know, something, 3 divided by 2 to the n, from 1 to infinity. So let's say this is our problem, and the way the ratio test works, you know what we're going to do? We're going to put this 2 to the n on top, and we're going to make this into n factorial. There we go. Much better. And the reason why I'm doing this is because I want to specify one more time that if you see factorials, ratio is the only test to use on factorials. So as soon as you see a factorial, you immediately know ratio. Cool. So your an is here. Now you might say, what about that minus 1? Don't worry about the minus 1 to the n. You're going to stuff this into absolute value. Absolute value is going to kill them all. All right? So don't worry about negative 1. We're just worrying about this. So we need to create an plus 1, which is n plus 1 cubed, 2 to the n plus 1 divided by n plus 1 factorial. So that was our an plus 1, and now we stuff all of that into the limit as n goes to infinity. So these absolute values that we have here are the ones that kill all of those negative 1 to the n or negative 1 to the n plus 1, so we don't need those. We're just going to have our n plus 1 cubed, 2 times 2 to the n when you peel off, n plus 1 peel off, n factorial stays, times the original problem flipped, because we will be dividing by it, and there we go. So now, n factorial gone, 2 to the n and 2 to the n are gone, and at this point, what you can do is you can cancel one of the n plus 1s over here, and what's left is the limit n goes to infinity of n plus 1 squared divided by n cubed, which is a 0, because you have a quadratic divided by a cube, faster growing function in denominator, so it's 0. There is also a 2 in front, but no one cares. times 0, right? So we have our ratio test. The ratio test, you get an plus 1 divided by original an, and then just take the limit and be done. So a lot of cancellations. I did this color-coded so you know exactly what cancels with what, right? And that's it. So now let's take a look at the root test. Now,
so
yes?
That was 0, it's less than 1, so it converges at 0.
No, it just converges.
Okay.
Oh, converges by ratio test. Sorry. Yeah, you have to write that, converges by ratio test, but it doesn't converge at 0. It just converges. There are only two tests where we know where they converge at. And that is, what are those are what two tests? Geometric and telescoping, yes. So you will know the sum only for geometric and telescoping. That's it. The rest of them you don't know the sum. Does anyone need the summary sheet of all of the tests? You all have them? You have one? You have it? Okay. All right, so the last test, so this sheet contains 10 tests, all of the tests. The last one we're going to look at is root test, and I just do it a little bit different, right, than what they do. I write it differently because you cancel the root before you take the limit. So you can do what they do on a sheet, or you can do it this way. So now we're talking about root test. The form is an raised to the nth power. And if you look at the sheet, it doesn't have to the nth power. And the reason why I do this is I'm going to first say, take the nth root of an to the n, and this is where they cancel. So now you just need to take the limit of an. So this is going to be equal to an, and now just have, just do the limit, n goes to infinity of an, and you have same three possibilities: less than 1, converge, more than 1, diverge, equal to 1, inconclusive. So same conditions as your root test. Same conditions as the root test, is just that you have to cancel this one. Now, the simplest example obviously are the ones that you can solve using other methods. You already know the answer to this. What is the answer here? Converges gives you 2 points out of 10. The answer converges is a correct answer, but it's also 50-50 guess from converges, diverges, right? So that's 2 out of 10. What else needs to be said for 10 points?
The sum.
You didn't mention which test you used, and you didn't mention.
No, I know.
You didn't mention the condition for convergence, since you said converges, right?
Okay.
So for the 10 points, you have to say converges by geometric series because r is less than 1, right? Your 2/5 is less than 1. So that's what you know from the first lecture on series, right? 10.3. But now, instead of that, we're going to take the nth root of 2/5 to the n and solve this problem the other way. And as you can see now, when you take the limit, n goes to infinity of 2/5, there's no n in it. It's 2/5 less than 1, converges by a root test.
I mean, in that case, though, for geometric series, you could just get the summation for it, right?
Yes, that's why geometric series is better, because every geometric series can be solved by root test and ratio test. But root and ratio can't give you the sum, which is why if you have a problem that can be solved by geometric series, you always solve it by geometric series to find the sum, because those geometric and telescoping series are great. Remember the telescoping series, we also had that polynomial, we did factoring, and then we did partial fraction decomposition, and for telescoping. You could have just looked at the problem and said, yeah, converges by limit comparison, like this. Why do extra work with telescoping? It gives you the sum at the end, right? So if you can do the problem with geometric and telescoping, you do the problem with geometric and telescoping, because then you know the sum at the end. Other 8 tests, well, divergence test diverges. So other 7 tests that converge, they don't give you the sum. So you want to, use the 2 that do if you can. Here's another problem that you already know how to solve. So what's the deal here?
You can do geometric again, since
Yes, excellent.
r is greater than 1, so it diverges.
Perfect. Diverges by geometric series because r is bigger than 1. Awesome. We can also do the first test that you should always check. First one on the list, which is the nth term test, which is the divergence test. The limit is different than 0. In this case, is infinity. Therefore, it diverges by divergence test as well. So we have 2 tests already telling us this diverges. We're just going to do root again because we can. Okay? So first step is to take the nth root of 3 to the n, which would just kill the exponent, and you just get 3. And now when you do the root test limit, which is limit of an, which is just limit of 3, well, that's just 3, and it's bigger than 1, diverges by a root test. Again, divergence test would take care of it, but you just want to, show off. So this problem can diverge by 3 different tests. Awesome, right? Now let's take a look at another example of the root test. Say you have a summation 1 to infinity of 1 plus 3 over n raised to the n power. What happened?
Sorry.
You just do the end root of the parentheses.
Okay, we can do that. We already did this problem in class using, can anyone remember?
It's e, right?
Yeah. So if you are to use divergence test, the first one, you would just get e cubed, and it would diverge by divergence test instantly, right? Because the limit is e cubed, that's different than 0, and we're done. But see, in this case, if you do the root test here, right, you get 1 plus 3 over n. And now when you take the limit of, as n goes to infinity, of 1 plus 3 to the n, 3 over n, what do you get? 1. And what do you know about that?
Oh, it's inconclusive.
Inconclusive. Right? So root test cannot determine convergence on this problem. But luckily the divergence test immediately takes care of it, right? So inconclusive root test. So you can run into these problems, right? And when you run into these problems, well, such is life, right? So inconclusive root test, use else. And we're going to go with the divergence test now. And that's simply limit of 1 plus 3 over n to the n as n goes to infinity is equal to, you were supposed to memorize this by now, e cubed. When you have that form, that's the e form. I will write it one more time.
I didn't realize that the fraction determines the power goes to.
I'm just going to write it now, just in case. 1 plus a over n to the bn is e to the ab. So now, whatever, you might have just a, you might have b, you might have both. And one of the problems where I'll put as a note, limit n goes to infinity of 1 minus 1 over n. To the n is actually the limit n goes to infinity of 1 plus negative 1 to the n. It's just a algebra black magic there. So it's 1 over e, all right? Still not 0, still diverges, right, in this case. And the root test would still fail, because if the n is not there, this part is 0, you still have limit of 1, so which is 1. So for the black problem underneath, right, with the note, that one would still diverge by the divergence test and still be inconclusive. What I wanted to show off is this plus and minus, and how you just move that minus, attach it to 1, and put the plus there. And it's still the same formula. So it's one formula whether you have a plus or a minus. This formula was learned in Calc 1, verified and used in Chapter 7, Calc 2, and now so this is the third time, right? And the final time. It's back in Calc 3, it's back in differential equations. So, make sure the orange one is it also makes a cool tattoo. Maybe you can do, diagonally across the back or something.
But then you can't use it on an exam.
That's true, but the person behind you can. Sharing is caring, so.
Then you have to be shirtless.
Well, I didn't go that far, but okay, fine.
Why can you make it?
There you go. Forehead. Either
That
way.
too.
Either doesn't work, right? Okay, cool. Well, that's it, guys, for Chapter 10. You've seen one test for sequences. You just take the limit. And I asked you to write that test for sequences on top of the page and say, test for sequences. Your sequence is just an. There is no sum. There is nothing. Sequence is just a list of numbers. So you were supposed to write on the top of the page, test for sequences an, limit of n goes to infinity of an is either L, meaning finite, converges to L, or plus minus infinity diverges, and that's it. So that's the only test for sequences we have. And that's supposed to go on the top of your chart here, and that's just sequences. Everything in the box is series. Series is the sum of the sequence, which is, we has that summation in front, and we have these 10 tests. We covered all 10 in sections 10.3 through 10.7. And the only thing that it's left for us is to discuss how to pick appropriate series, right? Because some problems on the exam will say, use integral test, or use root test, or whatever. And some will just say, check the convergence, which means, does it converge, does it diverge? And then you have to pick the test. Just like for some of the problems, right? You had to pick what is the correct integration technique, or in Calc 1, what is the correct derivative technique, right? So now you are picking the correct series technique. And that's chapter 10.